Good afternoon to all the audience. I'm Sam, a student from the University of Nottingham, Malaysia, and today I would like to present about the design of USV for search and rescue in shallow water. On today's topic, I will present about the USV Jetson Oro Challenger 1, the vessel shipwright overview, robotic algorithm, communication system, control system, and deep learning object detection. Here I would like to give a brief intro. An unmanned surface vehicle USV are a vehicle that operates on water without a crew. USV are remotely operated drones, or sometimes called as an autonomous surface vehicle ASV. USV can perform tasks such as a shallow water surveying, search and rescue SAR mission, transportation, environmental data gathering, surveillance, and etc. USV is not a new thing. As far back in the World War II, the US Navy used it for ocean warfare and anti-terrorism mission. However, USV for SAR development were documented in the 1990s. In this slide, I would like to address the problem statement for the project. Chances of survivability reduces over time when naval accident happen. Because of uncharted weather and current condition, time taken for search and rescue the victim became unbearable. The problem proposed the need of an USV built for SAR purposes. The importance of developing an USV is to reduce the risk of men, to save the precious life of frontliner, perform tasks which manned vehicle cannot done, act as a force multiplier for security operation, day and night operation equipment, and finally USV are cheaper than commercial ships. Therefore, we as a team developed the Jetson Oro Challenger 1 USV for the purpose of search and rescue mission in shallow water. The vessel is designed based on a single chine twin-hull catamaran design and is tested in the pool of the university. The vessel is 0.9 meter long and 0.6 meter wide with a displacement height of 0.2 meter. The vessel is fully watertight to prevent damages to the component. We integrated manufacturing, robotic algorithm, artificial intelligence, control system, and communication to develop Jetson Oro Challenger 1 USV. The features of Jetson Oro Challenger 1 include hydrodynamic body, heat distribution system, high speed, long battery life, high payload capacity, accurate localization, self-trained artificial intelligence, and a simplified PID controller for its mobility. In this session, I would like to discuss on the vessel design analysis and manufacturing overview. Here you can see the first and second phase of the manufacturing process. Let us move on to the simulation analysis overview. We use simulation software to determine the overall experience of wake cutting when the USV is deployed on water. We also simulated the hydrodynamicity of USV. The result were then used for the control system of the autonomous part on the USV stability control. This session showed the system architecture, which we use the NVIDIA Jetson Nano as the brain, connecting to Arduino Uno for the sensors and other electronic components needed. We developed our own PCB board to connect all the components with the controller and the brain Jetson Nano. To solve the heat problem on the Jetson Nano when we deployed the USV, a heat distribution system injected with water cooling system were designed to reduce the heat. The robotic algorithm focuses on autonomous navigation for robots, and it is practically and widely used in both academia and industry. It is categorized to three main algorithms: localization, mapping, and path planning. The mapping algorithm used is a Gaussian grid map, which utilizes the Earth sciences as a grid horizontal coordinate system for constructing the map. The algorithm converts the map into Cartesian coordinate from a 2D matrix of Boolean values. As you can see from the Google Earth animation, the university swimming pool is selected as the target mapping location. The mapping process consists of map selection, filtering, and grid conversion. Map selection is to acquire the important GPS coordinate on the Google map and obtain the scale in longitude per meter or latitude per meter. Next, map filtering is performed to filter out the USV movement region. The color malachite is filtered out and converted into black and white. Finally, the map grid conversion process is basically to convert the map into a matrix which consists of Boolean values. If the color is black, the value is 0, which means movable region. If the color is white, the value is 0, which means non-movable region or obstacles. Path planning is a task of finding continuous path that will drive the robot from start to goal configuration. Since a grid-based map is obtained from the mapping process, the grid-based search path planning algorithm A-star algorithm is applied. The A-star algorithm works by finding a path having the smallest cost to reach the destination using the two formulas shown. First, the algorithm reads the map from the mapping process, select the start and destination node, then it will analyze the 8 neighboring nodes, compare and select the nodes which has the smallest f value. If the destination is reached, optimum path is obtained by tracing back the route and the fastest route is determined. The path planning simulation simulates two scenarios with and without obstacles. From the result in the obstacle avoidance, the algorithm can recalculate an alternative route to avoid the obstacle. Robot localization is the process to determine where a robot is located with respect to its environment. We use Kalman filter as the localization algorithm, which is an estimation algorithm based on uncertainty measurement. In this case, for our USV, the factor causing the uncertainty includes satellite's position, atmospheric effect, and sensor inaccuracy. The Kalman filter works by performing estimation on the current state and predict for the next state using the state update equation and state extrapolation equation respectively. The device such as GPS sensor, MPU 6050 accelerometer, and gyroscope assist in the estimation and prediction process. From the flowchart, the algorithm first initializes the initial state and then perform prediction of the next state based on the accelerometer reading. After a unit delay of 4 seconds, state update equation is applied to estimate its current location with an input measure value of GPS sensor. Then it enters prediction state and then repeat its iteration process. The localization simulation simulates the uncertainties such as wind disturbance and GPS reading inaccuracy. The two graph plots out the true value, measurement value, and estimated value of the x and y axis in comparing the performance of the algorithm. The measurement value refers to GPS reading which has an error of plus minus 1.5 meter and is randomly selected in the simulation. With the application of state update equation, the GPS value is filtered to ensure the estimated location matches with the true location. As you can see from the figure, the yellow line is the displacement of the USV caused by the wind creating an acceleration in x-axis. Although the wind disturbance caused some error in the estimated value in the x-axis, the state extrapolation equation is able to predict the next correct state based on the accelerometer reading and the state update equation output. Moving on with the communication system, the system architecture shows that the Jetson Nano is connected to two Arduino using ARP protocol serial communication as the communication method. Both Jetson Nano and Arduino act as a master and slave in different conditions. The Jetson Nano acts as the brain of the system, giving command and instruction to the Arduino. The Arduino A oversees the movement of the board with the help of the control system as it is connected to the two motors and MPU 6050, while the Arduino B oversees the GPS reading and the heat distributor of the board. In the main program code, the Jetson Nano will send 12 instruction set to Arduino A for movement control. Arduino A will then return 4 instruction set to Jetson Nano as a method to synchronize the signal between Jetson Nano and Arduino. A and B is to notify Jetson Nano that the Arduino is ready to receive next instruction. C is for obstacle detection alert and D is for receiving acceleration value. E is for the receiving of GPS value. The development of the controller can be segmented into 3 parts: modeling, control, and testing. The approach to achieve the autonomous control of the vessel is shown in the flow diagram. First, control objective and variable will need to be identified, such as fast response time of the controller. Next, construction of system configuration takes place where the jet propulsion system has been used. Moreover, plant model was obtained, followed by the development of controller. Simulation and optimization of the model is done using Simulink. Lastly, performance of the controller has been analyzed from the result obtained. The jet propulsion system was employed for the motion and heading control with two motors each at a side. An IMU sensor MPU6050 was used to measure the output angular position with respect to the motor speed. For the vessel maneuvering control, the focus is on the 3 degrees of freedom, search, stray, and yaw model as shown in the photo on the right. Determining the vector representation of the motion is useful in this part. As mathematical modeling of the USV was complex due to the uncertainty and disturbance, offline plant model identification was carried out. For this project, the relationship between motor's input and the USB response was quantified during the on-water testing. A time domain input data was collected and MATLAB system identification toolbox was used to construct the dynamic system model from the obtained input and output data from the experiment. Transfer function was identified by performing gray box model identification. The development of a cascade PID controller was completed. The inner loop is employed to regulate the drive voltage applied to the motor. Meanwhile, the outer loop feedback works by comparing the current yaw rate with the desired yaw rate to produce a cross-track error. A reference was specified as a step change from 0 to 180 degrees. The simulation results shown in the photo prove that the USV heading angle meets the required step response by tuning the controller gains. The deep learning object detection has altogether 5 stages, which are data collection, transfer learning, model evaluation, optimization, and deployment. The challenges for object detection in our application is the outdoor vision. Therefore, the dataset prepared must contain a variety of images of humans with different sizes under different brightness and angle. We use the MS Coco dataset, which offer many images of humans with small size. Using the Coco API, a Python script was written to download 64,115 trained images and 2,593 test images. However, there are limited images of a drowning person. Therefore, we use a gaming design software Unity to create 500 training images and 100 test images. The transfer learning with TensorFlow is performed on an NVIDIA Titan 1070 GPU to obtain a customized SSD model. Using TensorBoard, we can observe the training of SSD MobileNet v2. The losses started at 11 and quickly dropped below 7. And finally, we obtained a consistent average value of 3.2. The training took 200,000 steps and 30 hours. The model is evaluated by finding the average precision. A high precision means the model classified no false positive but misses some true positive. A high recall means the model classified all true positive but also some false positive. IOU measures the overlap between two boundaries. The IOU threshold is predefined as 0.5 to classify if the prediction is true positive or a false positive. The test data for evaluation consists of 2,693 images with altogether 11,004 ground truth, the real object boundary. The average precision with IOU 0.5 is about 50.9, comparing to the average precision at 0.5 IOU of SSD 300, which is 41.2. We concluded that the average precision of our trained model is fairly high and acceptable. From the tracing, we can see the operations such as gather v2, con v2, and select were the process in the CPU memory, even though we tell TensorFlow to run everything on the GPU. As a result, our program spent too much time on data transfer and becomes slower. To solve this problem, we place all the operation in non-max suppression block on CPU because most of the flow control operation happen in this block. As a result, the total inference time is decreased from approximately 50 milliseconds to 30 milliseconds. The time cost for the gather v2 decreased significantly by about 65%. To deploy the model, a Python script has been written as illustrated by the flowchart. First, the boat performs detection by running machine learning model with camera stream. Once human is detected, the boat will be tilted until the target is located at the center of the camera. Then the boat will slowly approach the target and stop at a distance. Finally, the GPS of the target will be retrieved. As a conclusion, here's a short video summarizing the work we have contributed in developing the USV Jetson Oro Challenger 1. Within the video, you can see some of the testing we did in the university swimming pool. Thank you all for listening, and the following are the teams of developing the USV Jetson Oro Challenger 1. Thank you.